Hello everyone, welcome to the video of heat transfer. In this particular video we'll discuss about the governing laws of heat transfer. The governing laws are the laws which basically govern how the heat transfer happens in the different modes of heat transfer. It basically gives us the equations to describe how heat transfer happens in different modes. The first law is Fourier law. So according to this law, rate of heat transfer is directly proportional to area and the temperature gradient. So Fourier law governs give us the governing law for conduction heat transfer. So in conduction heat transfer, what happens? The rate of heat transfer will be directly proportional to the area and the temperature gradient. That means if the area of the surface through which the heat is flowing is higher, then the heat transfer will be the higher. And if the temperature gradient is higher, then the heat transfer will be higher. Or vice versa. So to make it an equation, we have to take out the proportionality and we have to put the proportionality constant, that is K, and the equation becomes Q is equal to minus of K A dt by dx, where K is the proportionality constant, and this proportionality constant is also known as thermal conductivity. This thermal conductivity is a property of the material which essentially tell us that if this property, that is thermal conductivity, is higher, that means heat transfer will be faster, and if the thermal conductivity of a material is lower, that means heat transfer will be lower. Then A is the cross-sectional area of the layer, and dt by dx is the temperature gradient. Temperature gradient means dt is the temperature difference. So in terms of instantaneous form, that is at a particular point, what is the temperature at a particular point, if we move along in the x direction, how the temperature varies with respect to x, that is what is your temperature gradient. So in finite form, you can say that this is temperature difference by length, that is thickness of the layer. And this negative signs, what this negative sign is used to ensure that the rate of heat transfer is positive quantity in the direction of heat transfer. So if we take the direction of heat transfer as positive, then the temperature gradient will become negative. We'll understand this better if we go through some problems. And this temperature difference will be negative. So to counter that, there is a negative sign, so that we can make the heat transfer is a positive quantity. So now let us look at this problem. It is a very simple problem I have given here. I urge you to solve it by yourself. That is, you have to consider a copper cylindrical slab of a cross-sectional area of 1 meter square and thickness of 20 centimeter, and the temperature of the left and the right ends of the slabs are 150 degrees Celsius and 50 degrees Celsius respectively. Then you have to determine the temperature gradient and the rate of heat transfer, and the thermal conductivity of copper is given, that is value of K is given 400 watt per meter Celsius. Here you should also remember one point, that is the unit of thermal conductivity is watt per meter Kelvin or watt per meter degree Celsius. SI unit is watt per meter Kelvin, since the difference in Kelvin and difference in Celsius is the same, so we can also write watt per meter Celsius. Watt per meter centigrade. So if we try to put whatever is the given data to the Fourier's equation that we have just learned, I think you will be able to solve it. So but the thing is, there are some assumptions involved here, that is the cross sectional area of the slab is constant. Okay, the slab is homogeneous and isentropic, and the thermal conductivity K of the slab is constant. So why this assumption is given? Because this thermal conductivity that we will see further changes with respect to temperature. Okay, it does not always remain constant with respect to temperature. That means if temperature is changes, the thermal conductivity of a particular material also changes. Okay, though it's constant, we assume it's constant for a particular material, but it changes with respect to temperature. Okay, thermal conductivity also differs from material to material, but for a particular material we assume it to be constant, though we'll see in some cases that it changes with respect to temperature. So this assumption is also very important. Okay, so assuming all this, I think you will be very easily able to solve this problem. So give it a try. Then the next law is Newton's law of cooling. This law gives us the equation for heat transfer in convection mode. Okay, so the equation is Q is equal to HA T minus T environment. That is, the heat transfer rate is equal to heat transfer coefficient into area of cross section into the temperature difference, that is delta T. Okay, the Q is the rate at which the heat transfer out of a body to the surrounding, that is, let us say it is made up of some fluid, either it may be water. Suppose if you dip a hot rod to a water bucket, what will happen? Okay, or if we put a hot rod simply in a room, how the heat transfer will happen from the rod to the air. Okay, so this H is the heat transfer coefficient of the surface. Okay, heat transfer coefficient of the rod. Okay, rod surface, and A is the heat transfer surface area, and T is the temperature of the object, and E and V is the temperature of the environment or the fluid. Okay, and delta T is nothing but the difference of both the temperature. Okay, this is what is Newton's law of cooling gives us. Okay, then the last is Stefan-Boltzmann law. Okay, Stefan-Boltzmann law gives us the law of radiation. Okay, this is E is equal to sigma into T to the power 4. So the Stefan-Boltzmann law states that the energy emitted from a black body, okay, per unit area per unit time is directly proportional to the fourth power of the temperature of that particular body. So here the EB is the energy emitted by a black body per unit area per unit time, and T is the absolute temperature of the particular body, and this sigma B is the Stefan-Boltzmann constant that we get from removing the proportionality. Okay, and that constant value you have to remember that I have given here, it's very important. It is 5.678 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, so these are the three basic governing laws of heat transfer that governs all the modes, that is conduction, convection and radiation. Okay, thank you.